Hello everyone. Today we are going to understand how embeddings work in machine learning. Okay. So computer doesn't understand text like we do. It understands numbers. That's why to communicate with computers we need to convert our texts into numbers. So here come the embeddings. So embeddings is the technique of converting something into numbers so that computer can understand. It can be text, it can be audio, it can be video, etc. Okay. So here, throughout the whole video, we are going to take texts as example to explain the embeddings. Okay. So here we can see cat can be represented as a vector 0.2. I have taken the single dimension for simplicity. It can be multiple dimensions. It doesn't matter. Then we have dog, we have apple, then we have orange. Okay. So now we are going to understand how this number was assigned to represent cat. Okay, so there are several methods. First, we are going to understand statistical methods. This is a traditional old method. Like this method normally doesn't is not used right now. Okay, so there are two techniques. One is term frequency, another is inverse document frequency. In term frequency, uh, when suppose in a page, okay, suppose in a page a word is occurring multiple times, so in term frequency that word is given higher weight. Like if it occurs multiple times, that word is given higher weight, and this is the main principle of term frequency. Okay, now what is inverse document frequency? In the inverse document frequency, uh, across multiple, like across multiple across multiple pages across multiple pages, if a word occurs rarely, then it is given higher weight. Okay, so this is the principle of inverse document frequency. So to summarize, if a word occurs multiple times in a page, term frequency gives higher weight to that, and if a word occurs rarely across multiple documents, not a single page, across multiple pages, then inverse document assigns higher weight to that. Okay. So this is statistical method. Now, one major problem of this technique is that it doesn't understand semantic information. For example, here we have cat and dog. You can see the weight that is given to cat and dog are similar. For example, here 0.2 and 0.3, they are close. But cat and orange, they are irrelevant things, and their weight distribution is also larger. Like the difference between their weight distribution is larger. So in statistical method, we cannot assign weight like this. It doesn't understand the semantic meaning behind each words. Okay. So here comes the modern embeddings. In modern embeddings, dense numerical vector represents semantic meaning of text. Okay. So we use dense numerical vectors which represents semantic information of text. Okay. So again, there are several kind of embeddings. Okay, so we'll now see the classifications. So first one is traditional word embedding, then we have static word embedding, then we have contextual word embedding. So these two embeddings are modern, and this is the traditional one. In traditional one, there are no semantic information, like it doesn't know any semantic information, or if it knows, it's very less. But in static word embedding, it understands semantic information. And the last one is contextual word embedding. It is dynamic word embedding. It doesn't only know the semantic information, it also can update depending on the context. Like it can update the embedding depending on the context. For example, suppose bank. Like bank has a weight, like bank, for example, again, suppose bank has a weight of 0.2 in one sentence, but in another sentence, depending on the context, its weight can be 0.6, 0.7, whatever. Like I am just giving this for examples. Okay. So basically, it can dynamically update its weight. Now, Before going further, we have to understand what is tokenization. Okay. So tokenization is a technique of converting a large unit into a small unit. Okay. So for example, here we have a sentence. Okay. Now this sentence into divided into words, right? So here each word is a token of the sentence. So and the procedure of converting these tokens is called tokenization. Okay. So going further, we will have to understand this tokenization. That's why I'm discussing this right now. Okay. So now here we can see word to vector was a it is an example of static word embedding. So to understand modern embedding further, we'll now understand how word to vector works. We have given an example, okay, algorithm. So here in the left side we have a neural network. Like it is a neural network. Okay, it is a neural network. So here we can see the neural network has input words like input side, then hidden side, then an output side. What this neural network does is this neural network tries to predict the middle word. Okay, so uh, so suppose it takes some words or some tokens as input, then it goes through the hidden layer. The hidden layer assigns some weight to each of the tokens, then it generates a output. Okay, so now here, one thing to notice that is that the output is not our embeddings. The embeddings is actually the weight. Like for the set of weight that our output is correct, the weight is given as input, as embedding. Like for the set of weights that we're getting our output labels corrected, the weight is given as embeddings. Okay. So we are getting our embeddings from these weights, not our output probabilities. It is just taken like it is just a measure to calculate the right weight. Okay. So here we have a sentence, for example sentence, this is a great book. So first we convert it into token. Okay. So this is a great book. It is converted into tokens. So there are total 5 tokens. Now, what our neural network does is it tries to predict the middle token. Okay, so that means we have to convert it. We have to pass it to the input. So we have to select some input and output. So in this sentence, we can select a context window of two. That means first two token will be input, then the later one is output, then the further two tokens will be our input. So and our model will see just these inputs and it will try to predict the output. Okay, so these inputs, like this is a great book, this is great book, these 4 tokens are passed through the input words, but again these are just texts, right? Computer doesn't understand text. That's why we have to convert it into vector. Okay, so here comes one hot encoding. One hot encoding is what it just basically converts each of these tokens into vector, and it uses this positional vector to encode it. For example, here if we label, like if we label each of the tokens 0, 1, 2, 3, 4 as indexes, then let's suppose we're trying to encode the each token. Okay, each token appears at the first index. Okay, zero base indexing. So each token appears at the number one index. So the number of indexes bit is set and the other bits are zero. Okay, so this is how we make tokens, or we make encodings, like the hot encodings for all the vectors, and then from this encoding, this is a grade book. Okay, so this is grade book. These 4 tokens, not a is our output. This is grade book. These 4 tokens are passed to the input. Now these tokens are vectors, right? So in hidden layer a matrix multiplication happens. Okay, so in hidden layer there are two stuff. One is the vector that we just pass through our input, and other one is embeddings. This embeddings is a matrix that initially contains random values, like random values. Sure. So what happens is this input is multiplied with the embedding, then we get a weight distribution, then we get a embedding for each of the token. We get the embedding for each of the token. Okay. So now, depending on the weight, then we combine all the embeddings, and these embeddings are combined to get our targeted output. Okay. So then weights are combined to get our targeted output. Then if our output is wrong, then a error is calculated and the back propagation happens, which updates the weights. Okay. So here we are updating the embeddings depending on our error. So after several iterations, we get something like this. Okay. So this is a score that we provide to each of the tokens. Then each of the token goes through softmax function. This softmax function converts each of the weights to probabilities. Okay. Now through this probabilities, the highest probability vector, the highest probability value is taken as the output. Okay. So that means our model is predicting A. So that means our model is correctly predicting the middle word, and the weight, the weight for which the model has given us the correct output is taken as the embeddings. Like these are the embeddings. Sorry. So here, these are the embeddings. Okay, embeddings. So this is how embeddings works in machine learning.